Thank you, Yevgenia. It's a pleasure to be here. Well, at least virtually, I was supposed to come, but okay, life is not straight path. So sometimes it twists a bit, maybe like this, and I had to stay. So well, anyway, thank you to all the organizers for inviting me here, and I will talk about this two-phase problem in VMO. This is joint work with Tolsa. And okay, let's move to the matter. I will try to make a bit quick introduction. I hope I am not too fast, but most of things have already been presented by many of you. So it's like talking all the time about the same things. Maybe I will try to be a bit quick about this first part. So first I will talk about harmonic measure. As you know, this Dirichlet problem is solving this equation with boundary data f. If the f is continuous and the domain is good enough, there is a continuous assignation given by the pointwise value evaluation of the extension. And then there is a unique probability measure, which is written omega z. This means a harmonic measure with pole at z. Okay, and now, different poles will give rise to mutually absolutely continuous measures. So for the problems we are dealing with, we don't care about the pole, and Z will be neglected all during the pole. Okay. Now, questions about harmonic measure from the metric point of view or geometric point of view. What is the dimension of the support of the harmonic measure? And the support here is not exactly the support in the usual way. So let me just, I will give you some idea later. When it is omega mutually absolutely continuous with respect to surface measure, we will be working in Rn+1. So this is the n-dimensional Hausdorff measure. And what are the connections with rectifiability? Okay, some answers in the plane. For instance, if omega is simply connected and finite length, then they are mutually absolutely continuous. No, in this case with length. This is the famous Riesz brothers theorem. There are other results in the complex plane using complex analysis, Carson, Makarov, Jones, Bishop, Wolf, Garnett, and so on, and so forth. And all, but when you go to higher dimensions, for instance, the Riesz theorem fails. It's not true anymore that simply connected domains will have this relation, and we need real analysis techniques to deal with that. Now, let's recall what is an NTA domain or what is not an NTA domain. This is not an NTA domain. So you need given 2 points. Let's say this one, these 2 points, you can find the connection by circles, and the number of circles depends with this fraction. No, this the distance divided by the distance to the boundary. The omega here is the distance to the boundary. Also, there is this corkscrew condition is that for every ball centered at the boundary, you can find balls inside and outside with comparable radius. Here it fails because in the cusp, the outside ball is every time smaller. So this is not corkscrew domain. And NTA domain will be a domain that satisfies both conditions. For instance, this one, the von Koch snowflake, as you can see, satisfies both conditions. At least you can intuitively see that. So harmonic measure is traveling in NTA domains, and its support coincides with the whole boundary. Okay. So what are we talking about? Well, the dimension of the support. What is the dimension of the support? It's nothing. The dimension of the support is the dimension of the boundary. So what we want to understand is the dimension of the minimal set that contains all the harmonic measure. So such that the complement of this set would have harmonic measure 0, and this can be of dimension smaller than the dimension of the boundary, as it is the case with the von Koch snowflake. Okay. Now, what is the one-phase free boundary problem for harmonic measure? It consists in characterizing geometrically the absolute continuity of the harmonic measure with respect to the surface measure. So we have already talked about this in other talks. Let's say this first result by Dalberg, which says that if the omega is Lipschitz domain, this is geometric information, then we have that the density of omega with respect to sigma is satisfies a reverse Hölder condition with exponent 2. This is the reverse Hölder condition. Okay, so this means that of course the reverse Hölder, because in this way it's always true without the constant. of course, but reverse Hölder means that paying the price of putting a constant, you can just reverse the inequality and get this. Okay, it's the reverse Hölder with exponent 2. And in particular, reverse Hölder, whichever exponent it has, it implies the A infinity condition. That is just this is just a quantitative way of saying that the harmonic measure is mutually absolutely continuous with respect to surface measure. Okay, so this is the first result, one-sided result in history in this harmonic one-phase pre-boundary problem, the harmonic measure. And then this other result I want to mention by David and Jerison in the year 90. This if omega is a chord-arc domain. This means that it's NTA as before, and moreover, the boundary is n Alfors-David regular. It means that the surface measure increases as a power of n with the radius of the ball. Then we get the same conclusion. No? So this is like a generalization of Lipschitz domain in this setting. Okay. And now I want to mention also a recent breakthrough that I will not deal with, but during the talk, but at least just mentioning because I think it's important enough. Is the geometric characterization of Wiga infinity, and this is related to Dirichlet solvability. And already some speakers before me, even today, have mentioned that. So I won't dwell in this, just for the sake of completeness. Now, two-sided results. What is the two-phase pre-boundary problem? Two-phase pre-boundary problem, we want to characterize this the mutual absolute continuity of two harmonic measures. So now we have a domain omega plus and omega minus, which would be omega plus complement. Okay, and now we have a harmonic measure from the inside, from a pole here, and from the outside pole here. You gave rise to two different harmonic measures, and when they are mutually absolutely continuous, what geometric conditions on the boundary imply this? There is this result, quantitative result again, by Azam, Murvoglu, and Tolsa, that says that if omega is NTA domain and the complement is NTA domain as well, then it's equivalent to be A infinity. It's equivalent to both harmonic measures, exterior and interior, having very big pieces of uniformly and rectifiable measure. Okay. And this is also equivalent to both domains, interior and exterior, have joined big pieces of chord-arc subdomains. So what does this mean? This big pieces idea is, okay, now we are with respect to harmonic measure. This big pieces idea is just for every ball, the boundary satisfies, so you can take a subset E in this ball B such that the measure of the subset is greater than a constant times the measure of the whole ball, something like this. And this subset should satisfy this thing. And when we say very big pieces, it's like for every epsilon, you can put here 1 minus epsilon, and paying the price that the constants for the property may get every time worse, but you can get some constants for every epsilon so that this happens. So at the end, you kind of exhaust the every ball, but just paying the price of getting worse and worse constants. Okay, this is very big pieces. So these two things are equivalent to just being well, mutually absolutely continuous, quantitatively. Okay. Next, well, uniform rectifiability. I have to mention this. You already have heard many times what is an IDR, so Alfors-David regular, and the image is like almost everywhere. No, sorry, in a big part is contained in the image of a Lipschitz function. Okay, and the constants are uniform. These constants are uniform. This is uniform rectifiable. Now, there is a non-quantitative version. So of this theorem is just one implication, I think. Is so whenever both harmonic measures are mutually absolutely continuous, then this implies that almost everywhere, with respect to the harmonic measure is mutually absolutely continuous with respect to the surface. So when the measure from the inside and from the outside are mutually absolutely continuous, then this needs to be somehow flat. At least it's absolute. So the measure is comparable to the Hausdorff measure. Okay, the surface measure. So far, so good. Let's move on. Okay, Now I need, in order to go to the problem I will talk, as you recall, it's not only free boundary, two-phase problem, but moreover is for VMO. And this VMO problem is related to Reifenberg flatness. So we attack it in the Reifenberg flatness setting. What is Reifenberg flatness? So when we have a set E, take a ball, and then you just put a strip so that the distance is bounded by delta, let's say, and when you divide by the radius of the ball, so in a scale invariant way, but in both directions. So the distance from the straight line to the set, and the distance from the set to the straight line. It's like a bilateral beta. This kind of issue. Okay, there cannot be holes. This would have a very big beta. Okay, this would have a beta like that because it's comparable to this distance. Okay, it's flat and it's like long. Okay, now what is a delta Reifenberg flat? Delta Reifenberg flat tells you that at every point, at every scale up to a certain order R, this bilateral beta is bounded by delta. And moreover, this strip that covers the set, separates interior and exterior of the domain. Let's see with a picture, it's more clear. As you see, when you put the best approximating plane and you take the strip of width delta, you get exterior and interior part, and they are separated by this strip. Okay. Now, small delta implies in particular that omega is NPA domain. Okay, and we say that omega is vanishing Reifenberg flat if it is Reifenberg flat for every delta. Just of course, at every scale, for every delta, we get a worse radius, so a smaller radius. Okay, so there is like this kind of model of continuity with respect to delta. At every time you have a smaller radius. Okay, good. Let's move on. Now, well, this is notation. Given a random measure, we just write the mean or the mean for the mean. These three things are the mean of a set. And now we introduce VMO. VMO is just says a function is in VMO of mu if this limit goes to 0. And what is this limit? This is just for every ball centered at the boundary and with radius r. Well, no, centered at the support of the measure, sorry, and with radius r. Then this mean. So the function you measure the oscillation of the function around its mean in the same ball. Okay, so you see how does the function oscillate on the mean. So the function is like this. You take the mean and you measure in the L2 way what is this distance. Okay, and this would be the VMO, like the VMO norm. And you see that when the radius go to 0 uniformly, you have this quantity going to 0. You can also write this in the following way. This is the VMO norm. Means like VMO norm inside the ball with respect to mu. Of course, this is with respect to mu. Sorry, this shouldn't be here. Yeah, with respect to mu. And here it's like, it would be for every ball inside the ball B, or for every cube inside the ball B, this quantity here is smaller than this constant. And now this constant, when you go to 0, is every time smaller and smaller than this is the same. This and this is the same. Okay. Now, asymptotic absolute continuity. Next idea. I'm sorry that a lot of introductory steps, but I guess we will soon be into mathematics. Okay, let's say given a weight W in a doubling measure space, Corey showed in a paper in the 90s, I think, or 80s, I'm not sure, that the following asymptotic weight conditions are equivalent for every p greater than 0, greater than 1, maybe. I'm not sure. Put greater than 1 just in case. Okay. The limb sup of this VMO norm as the radius goes to 0 uniformly goes to 0. So this means that logarithm of W is VMO, as we said in the previous slide. Okay. Now this condition, the logarithm of the weight being in VMO, is equivalent to this one, and this one is related to the following. So mean of Q omega mu is smaller or equal than this. This is just the Hölder inequality or Jensen. No, this Hölder inequality. The reverse thing you have to put a constant, as we said. No, this is a reverse Hölder. And now if this constant goes to 1 you increase scales or you decrease in scales, then this is this condition here. So this is kind of vanishing reverse Hölder condition with exponent p. Okay. Now vanishing reverse Hölder with exponent p is equivalent to the logarithm of the weight being in VMO. On your right. Okay. This is what we have said. Vanishing reverse Hölder with exponent p for every p is equivalent. So in particular, for 1p, you have all possible values of p with different modulus of continuity, of course. Okay, but all of them are equivalent to the logarithm in VMO. Good. And there are also other conditions equivalent, but we don't care about this. One is the AQ weight and the infinity weight conditions and asymptotic weight. They are also equivalent. And that's why it's called asymptotically absolutely continuous. So we say that omega is asymptotically absolutely continuous with respect to mu, and we write it like that. Okay, if they satisfy all these conditions. And we will only work with these two. Okay. Good. Now, let's just explain what is the one-sided problem for VMO. These are resolved by a series of papers by Kenig and Toro, 97, 99, and 03. Says that if omega, combining all these results, I mean, it boils down to the following result, or you can just extract the following result. If omega is a bounded chord-arc domain, which is δ-Reifenberg flat, and delta is small, you take omega to be the harmonic measure in omega, and both p, whatever, and write sigma to be the surface measure. Then the following are equivalent. The logarithm of the density is in VMO with respect to sigma, if and only if the inner normal exists and belongs to VMO. Okay? The normal belongs to VMO of sigma. Both conditions are equivalent. And moreover, you gain by 3 that omega is vanishing Reifenberg flat. This is by 3. So you have A and B imply in particular that omega is vanishing Reifenberg flat. So what is the two-sided VMO problem? And this is where the result that I am presenting today with Xavi, it was published 2 years ago in this calculus of variation and PDEs. The following: you take a domain in Rn plus 1, it's a bounded NPA domain, and both the complement is NPA as well. And you suppose that it's δ-Reifenberg flat with delta small enough. Now, the following are equivalent. First, the density is in VMO as before, but now with respect to omega plus, okay, the logarithm of the density is in VMO with respect to omega plus. That is what, as I said before, since omega minus is asymptotic, absolutely continuous with respect to omega plus. Good. This is equivalent to omega plus being vanishing Reifenberg flat, and being existing omega almost everywhere and being in VMO. And moreover, you need this extra condition that omega plus satisfies a reverse Hölder inequality of exponent 3/2 with respect to omega minus, or vice versa. You can both conditions are enough and are implied in this. So one gives the other. Okay. Well, in A implies B, I must say that vanishing Reifenberg flat was already shown by Kenig and Toro in this paper in Querelle. So this is already proven. And this in particular implies this. So we only need to prove that thing here. Okay? For A implies B, we only need to prove that N belongs to VMO. Okay? This is our contribution. And in the other way, I mean, there's only one thing to prove. So that's all. And now, just for the sake of completeness, this is equivalent to maybe a slightly more geometric idea. Is that vanishing? Well, omega plus is vanishing Reifenberg flat. Omega minus is infinity with respect to omega plus. And you can, instead of taking VMO, recall that in VMO you measure the oscillation with respect to the mean. Instead of the mean, you can put this NB, and this NB is just taking the interior normal from the vanishing, sorry, from the Riesztransform flat condition. So you have a domain here, you have the best plane, and this normal vector, which is the normal to the best approximating plane, this is what you put here. Okay, you don't need to compute a mean. So this is a geometric thing here. Okay, and this is quite geometric because we already have that this is equivalent to omega plus minus having joined the thesis of product subdomains as I have told you before. Okay, so this is quite a geometric stuff, but we this follows more or less quickly from this, at least just modifying slightly the proof. But what we will look at is this this relationship. Good. So just to mention the vanishing, sorry, the Riesztransform flatness is necessary. Why? Consider this this domain in R2. So in the complex plane, this is not a domain because this and these are separated. This is not a domain. It's not connected. Okay, but in R4, if you define the same kind of inequality, then both sets, interior omega and exterior omega minus, no, omega plus omega minus, would be connected in R4. And in this case, then we fall at infinity, then the harmonic measure omega plus and omega minus are exactly the same. So this logarithm, if the logarithm of 1 is 0, so it's always in VMO. But the normal vector in the center does not satisfy a VMO condition. Okay. So Riesztransform flatness is necessary in order to obtain this n belonging to VMO. Okay. Otherwise, singularities may spoil your picture. Okay. Let's move on for some preliminaries. So first definitions. Omega is the harmonic measure. Omega minus the harmonic measure. Omega or omega plus is the same. Okay. Omega minus is always denoted with the minus sign. Then theta is this kind of density of a ball. So just the measure of the ball divided by the surface measure of its boundary. Now, theta, if it's applied to a point, is just the density. So the limit when r goes to 0 of these thetas. Maximum Hölder operator is the same as always. So here, what you measure here with respect to omega. Okay, so you put here omega. Then we also talk about the maximum operator of measures. That is just the supremum of this in all the scales. Okay. And then you have analogous definition for theta minus, omega minus, and so on. So for the exterior part. Now, given a radon measure, you can take the n dimension of this transform as usual with this kernel, working against the measure of nu. And whenever this makes sense, sometimes it doesn't, but these always make sense if the measure is, let's say, finite, I guess, or a bit more general also. This just truncating. This is the truncated Riesz transform. Okay. So here we avoid the singularity, and R star will be the maximal Riesz transform. So you take the supremum amongst all the truncated possibilities. You also write R mu f equal R times f mu. Okay, I'm not sure. Yes. Well, anyway, yes, it appears. So it's just like that. So it's just the Riesz transform as always. Okay. Next, okay, the CDC condition and tangent points. I am not telling you what is the CDC condition now, just feel that it's NTA, but this is also valid for CDC. And NTA domains are CDC, so this is what you need to retain. Every pair of NTA domains with common boundary and with omega plus and omega minus mutually absolutely continuous by Asymptotic Tolsa satisfy the following. The boundary has an n-rectifiable subset with full harmonic measure. This is the two-sided non-quantitative pre-boundary problem. Okay. Moreover, both harmonic measures are mutually absolutely continuous with respect to Hausdorff measure. Fine. Good. Moreover, all points in F are tangent points for the interior for the boundary. Okay. So this means that it's like you have this. You can approach them like with cones of every given amplitude. And there will be nothing inside. And F this set is dense in the, well, of course, this is a consequence of they have full harmonic measure, so they need to be dense because the harmonic measure is supported in the whole boundary. Okay. Now, the unit normal is defined omega almost everywhere, which comes from here. Okay. And then being unrectifiable, I haven't told you what is this. You already know probably. It means that it's almost everywhere with respect to surface measure contained in a countable union of C1 dimensional manifolds. Okay. More definitions. I'm sorry about that. There are like there's a lot of background to move on. But now I am reaching the end of the background. Now, jump formulas. Final idea. Assumptions of the theorem do not grant that Hausdorff measure is locally finite. So traditional jump formulas are not available in principle. But a recent work by Tolsa provides jump formulas for a bit more general sets, in particular rectifiable sets. And in our setting, they say exactly the following. These jump formulas are for for a more general family of Hölder internals, I guess. But here, applied to the Riesztransform, we get the following. The Riesztransform approach non-tangentially from the outside minus the Riesztransform approach non-tangentially from the inside. So here you have omega, you have a point X. You take like a cone as Murgoglu defined, Michalis defined yesterday. No, you have these cones, and you approach from the inside and from the outside, and this would be these limits. Now the difference between both limits is exactly this. So the density times the normal vector. Okay, omega almost everywhere, and the addition is twice the principal value Riesztransform. Okay. Jump formula. This is very useful. This is a key idea in both groups. A implies B and B implies A. Okay. Okay, let's think why A implies B. I will try to give you just the scale of the proof. Let's see if I am able to do that in 10 minutes. I hope so. This is okay, this is a challenge. So omega is doubling, then you can define a dyadic structure. So you can define, we will define a good set and a low density set. I will tell you later what are they. But they are just a part of the cube Q, of any cube Q from the dyadic structure. Now, what we want is to control the oscillation of the normal vector with respect to a constant. Now, this integral can be separated into the bad set, the low density set, and the good set, which is not low density. We have these three regions. Now, we have the following formula. We will choose CQ, the constant, to be this one. So this is the mean divided by the absolute value of the mean. And then, of course, this is unit, and this is also unit. So it makes more or less sense. And we will use the following algebraic idea that when you take the difference between two normalized vectors, you can control by this. This is algebra, and you can check it. Now, if you plug this, so this formula gives you exactly that one. So theta n divided by n would be this part here, and the mean of the function divided by the absolute value would be this. So using the previous one, and since u is already the modulus of u is precisely theta, then you get this. Okay, this is automatic. Now, away from the low density, that's why we distinguish the low density part. We have that the density is big. No surprise, and we will use that. So we separate these three integrals, and now we have three regions. The integrand is unit thing. It's 1 minus 1 is at most 4. Okay, it's at most 4 because it's a squared. So you can bound this by the measure of this set plus the measure of this set plus this integral. And in this integral, you use this inequality because you're away from the low density part. So you get automatically apply this thing here, and you get this thing here. Okay. Now theta of q can substitute theta x because we are not in the low density part. We are in the high density part. Okay, so in this way, we have gotten this. And at the end, we need to control this by epsilon times omega of q. This plus another by another epsilon times omega of q. And this also by some epsilon, well, tau will remain here, but will depend on epsilon 2, so that we can play around with constants. And this will be all together, putting the constants in an appropriate way. You get that this is smaller than epsilon times q. That is exactly what you want to show. This tells you that and the normal vector is in vanishing in oscillation with respect to omega. This is the proof. Now there are some gaps that I haven't told you. Now I will explain you about some things about these gaps. Okay, what have we used here? Well, we need, of course, epsilon goes to 0 uniformly on the length of the cube. Okay, what have we used here? We have used the following. First, the low density set contains all low density points. That means that away from the low density set, you are big. Second thing, the low density set is small. Third thing, the bad set is small, so the good set is big. Okay. The third thing. Fourth, the Riesz transform does not oscillate too much in the good set. This is the fourth idea. So we need to show these four items. If we have these 4 items, we are done. Okay. This will be the definition. We have to pick wise definition in order to obtain this, and this will be a bit more important. Okay. Essentially. Okay. Let's talk about the low density set. Low density will be the maximal family of cubes such that the density is small. Okay. Of course, in the complement, the density will be big. So by definition, we get the first property that we need. Second is this lemma. So we need to see that the omega, so the harmonic measure of the low density part is more equal than epsilon times the measure of the set. Now this is done. I just give you a hint. This is not done by induction in scales, finding big pieces of n R+W regular sets. Okay, and this is obtained just using a local version of the Riesztransform problem, which was written by Riesz and Tolsa some years ago, and then we apply some Vitali type arguments. And in order to use this result by Riesz and Tolsa, you can find it in the paper if you want the precise statement. But you need 3 things, well, 5 things, to be to have small deltas, no, small beta numbers, but this is already because the set is Reifenberg flat, and then there is something about the density away from the ball, but it's also easy to do with some results by Kenig and Toro. So what we really need to prove are these 3 elements. We need these 3 ideas. First, we need to define a good set inside the ball, such that the bad set is small. The maximal operator on measures plus the Riesz transform, the maximal Riesz transform, also both are bounded by this theta of the cube. And the oscillation of the Riesz transform is bounded by theta of q squared. Okay, we need this. If we check these 3 things, we get automatically that you have like big pieces of uniform rectifiable sets. This is David Sem's idea, but in particular they are and R+W regular. That is what we use in our proof. Okay, so we get more than what we need. In fact, move on. Let's move on. Okay, now our assumption. What is our assumption for the good set? The assumption for the theorem is that the logarithm of the density is in VMO with respect to omega. So the oscillation of the logarithm of h vanishes uniformly. Now we use this for the definition of the good set. Our good set, our first approach to the good set is this one. So take the points in the cube such that h of x divided by aq minus 1 is small. What is aq? aq is this thing. And by John Nirenberg, asymptotically, this is the same as writing this. Okay? Asymptotically, at least. So what you are doing here is somehow, if you plug this here, you are like subtracting h minus the mean, but h minus the mean is exactly this information here. So it's natural that this good set is growing more and more as the length of the cube is smaller. Okay. Eventually, it's everything. Then we modify this to get a good set, a modified good set that satisfies a bit more properties. In particular, it's always big, okay, in this sense, and it needs to satisfy this thing. Okay, this is what we asked in Tolsa theorem, but also this implies by a TV theorem of Nazarov, Trell, and Bolberg that the Riesz transform is bounded in L2 with respect to this good set. Okay, if you have this condition, implies this thing here. This is a TV theorem. Okay, and in particular, this also implies a T1, well, weak one boundedness that we use in our proofs and so on. But this is like important. This is an important estimate for us. Okay. Okay. Now let's see the jumping identities. Okay. By definition of harmonic measure, this is just using the definition purely. The definition of a harmonic measure implies that if you evaluate outside the domain, the inside measure, so the Riesztransform of the inside measure, you can use the definition of harmonic measure and you get that is the evaluation, just the evaluation of the kernel. Okay, and if you are inside, then in the outside, sorry, if you are inside, the measure from outside also satisfies this kind of thing. So this is like very easy. This is an exercise. You can try it. It's just a 10 minutes problem. Now, if now almost everywhere with respect to harmonic measure, we have the jump formulas. Okay, these jump formulas, that and that. And moreover, if you approach non-tangentially with these ideas, you get also these equalities. What is this? This is non-tangentially from the outside, approaching the inside harmonic measure, and this is non-tangentially from the inside, the harmonic measure from the outside. Okay. So you approach this part of the Riesztransform is well controlled. So this is plus, this omega is of course is plus, as I told you before. This is plus, this is plus, this is plus, this is plus. But this is good, and this is good also. This is this one. Yeah? So what is really important here is this guy. This guy is the main one. Okay. So writing all together, we have find out that theta times n is just the Riesztransform from the inside, so the non-tangential Riesztransform plus something that is very good. And the principal value Riesztransform is also the Riesztransform from the inside plus plus something that is very good. Okay, I'm not sure that the constants are right. Maybe I made some mistake there. But well, of course, I don't know. Yes, they are right. They should be right. Well, whatever. You just can reduce the oscillations that because if you recall, both for Hirela-Sarrion and for the main argument, we need to control the oscillation. In the main argument is the oscillation of theta n, and in the David-Sims problem is the oscillation of the Riesz transform. So both to control both, we just need to control the oscillation of these guys, Now you define like the good set for lambda begin off. Just for every given cube you amplify the cube a lot, and then you get we get this lemma. It's just that whenever the length of cube is small enough, then we control the oscillation. That is exactly what we do. And this is the key idea. The key idea is showing this lemma. Once you have this lemma, all the other details can be filled. And to prove this lemma, we just use jump formulas, weak boundedness of this transform, point with control of maximal operators, some estimates of the good set that we have introduced before. And notice maybe because if you have doubts, what is lambda here? Lambda is used to separate the local part and the non-local part in certain typical Calderon-Zygmunt estimates of diagonal. Okay, so this will get small if lambda is big enough, and then you will get this epsilon. That's maybe roughly the idea. Okay, I have just I guess I have still 5 minutes. Is this right? Or should we go for questions already?
You still have about 5 minutes.
I didn't understand. Do I have 5 minutes?
Yes, you have about 5 minutes.
Okay, good. So maybe I can give you a hint about how B implies A is done. So let's talk first about approximating domains. Now we will have again a good part. It will be defined in a different way than before, but you will have just a good part in the boundary, and you perform a Whitney argument, a Whitney covering, as always, no? Well, a typical Whitney covering. But now you just put this extra thing. There's a maximum size. Well, this is technical detail. There's like a maximum size for the Whitney cubes, but otherwise it's a Whitney covering. And now you select the cubes that intersect the boundary of the domain, and now you amplify them with balls. Notice that here the distance of Whitney cubes is essentially delta squared times the length of the cube, and here you put balls that are delta -1. So it's like there is one scale. There's a change of scale here. Okay, and now you define the domain just by joining to this was, let's say this was omega plus, this was omega minus. Then you join the balls to get the big inside domain. The big inside domain and the small outside domain, and you do the same, just pulling out the balls, you get a small inside domain and a big outside domain. So you have all these elements here. Good. Okay. This is, I think, is Tolsa, Zam, and Murgoglu. They showed that this domain is again delta-Reifenberg flat if you play well with the constants, and moreover, locally, in the modified zone, the domain, this is not good. Locally, in the modified zone, you have a Lipschitz graph. Okay. Of course, the new domain, the modified domain, will not be vanishing Reifenberg flat because there are angles here. There are angles appearing, so it's not vanishing Reifenberg flat anymore. But when we are playing away with constants that get smaller and smaller and so on, it will be delta small, the delta will depend on the other delta, and so on. So there is a quantitative relation between what you have gotten and what you had before. Now, what we want to see, recall, now our assumption is that the normal vector is in VMO, and we want to see, and so on, and the other assumptions, we want to see that you have this relation. And in particular, we will use the equivalent definition that it's vanishing reverse Hölder for a certain exponent p. We have to check this. If we check that it's vanishing reverse Hölder for a certain exponent, we are done. Now, how to do that? We have this. We want to control this, and we want to control this by a constant 1 plus epsilon, and this epsilon has to go to 0 with the scales. Now we select a good set, and this good set now will be just putting away the low density and the high density. Just take away both bad sets, and you get a good set. No? Now here you separate the good part and the bad part. Now in the good part, you just switch harmonic measures, and this can be done by the maximum principle because just you are amplifying the domain somehow. And in the other side, you just will apply the reverse Hölder inequality because you already have that it's omega minus is the infinity of omega plus. So in particular, because this is one of our assumptions, and in particular, you get this reverse Hölder with a certain exponent q, and this reverse Hölder inequality. So if we show that this is small, you can show like by usual arguments, you automatically obtain this inequality. And this is very nice, but here we have to work a bit. Let's talk about this part. Okay, the key identity will be to prove this, that the normal vector is in VMO now, but with respect to sigma. Okay, and this will be like a small. Once you have that, you can apply the Kenig and Toro result for chord-arc domains, and you get that you have vanishing that sigma is vanishing reverse Hölder, and also omega minus is vanishing reverse Hölder for the exponent that you want. In particular, we choose 3 and 4. And now of course, we wanted to control this. This is exactly the same as this, just by breaking this here. And now you apply Hölder inequality and play around, and you get this inequality. And now these conditions, here you have a 4, here you have a 3, you apply this, and you get this equality, which is exactly this. So here we haven't done much. We haven't done much here. Okay, this is controlled by this. Now we can combine with the previous idea. Okay, so this goes for this. Okay, and this is what we had before, the same thing. So now, if we can control this by a constant, and we control this by a constant, we will have exactly this. That is what our objective. Okay. So now let me just say, because it's already maybe a bit late, that to obtain well, and this is more or less easy. This is not this is not very tough. To obtain the K-estimate, the idea is to control this difference, no, the normal minus the mean. And again, this is done using the same idea as before, of putting this again the normal times the density, and this again using jump formulas is related to the Riesztransform. Okay, so again we use the jump formulas, Hölder continuity of harmonic measure, and the boundary, change of pole formulas, approximate formula, some domain properties by a very nice paper of Kenig and Toro, and then the hypothesis. This strange hypothesis needs to be used here. This deeply has extra thing. So I guess that's all. Vielen Dank, Nagün, Sieben, Kitos, Pablo, muchas gracias. Pasiva, I think I finish here. For sure. Thank you very much.